Hi guys, today I'm gonna talk about Umklapp scattering. Actually, today's video have no any heavy and mathematically intensive equations, so you can just enjoy it for fun. Umklapp scattering is exactly this equation. If we remove the g vector, then it is same as the normal scattering, which is just the scattering between the electron, and we denote electron by k and phonon by q, and this is momentum, concept of momentum. We should leave some very basic concept. First of all, we should know about the Fermi free gas. Free gas is exactly means that there is no any potential energy, and the reason is we only treat the covalent bands electron. Then the electrons in covalent bands cannot feel the potential energy, electromagnetic potential energy of the nuclei, so we can just ignore it. So we just only have to consider the kinetic terms. And Fermi means electron is fermion, like as you guys know. So if we include spin term, then only two electrons can occupy same k number. Many-body system can be determined by the occupation number and whether it is fermion or boson. In this case, we only treat Fermi gas, so we can write eta as a -1. So what we have to know is just know the nk occupation number. And there is, if we assume the thermal equilibrium state, then there is a very wonderful formula from the grand canonical formalism, and we call this Planck formula. In this case, we assume the thermal and same chemical potential, same thermal, same temperature, and same chemical potential. Then we can get this equation. However, without any statistical mechanics skills, we can just intuitively induce this formula. First of all, if T is very low, then we can think every fermion is in the base state. Actually, this is discrete, as you guys know, so there is n particles, and if temperature is like a room temperature, then only thermal energy can excite the electrons here, from here to here. So we can imagine or anticipate the thermal heat capacity like this, and it is proportional to T linearly. Secondly, if T is very low, then the mu chemical potential will be positive, which means it is very hard to increase the occupation number. And if T is very high, then there is enough kVt, which is thermal energy. So kVt is very high, then we can excite the low state to high state, and we can get another particle, a new particle. So without this, even without this formula, we can imagine and anticipate the same result. Second, what is the Q and G exactly? They are both of them are crystal vibrations momentum. However, why do we separate Q and G? Because Q is microscopic notion and G is macroscopic notion. According to Debye model, the biggest momentum is smaller than G. So, and generally Q is way more smaller than G. So Q is very small, so Q is very macroscopic notion. And secondly, the relationship between Q and W, which is dispersion relation. In this case, omega Q plus G is equal to omega Q, so we cannot distinguish Q plus G and Q. So we have to define the phonon in the range of smaller than G. And the real physical meaning is crystal vibration, so only K plus Q plus G is conserved. K plus Q is not conserved, cannot be conserved. You should remember it. So finally, I will explain why Umklapp scattering can effectively make resistance and participate in the resistance. As you guys know, as you guys can see, normal scattering cannot effectively change the direction of K. Only Umklapp scattering can change the direction of K almost pi degrees. Only Umklapp scattering can participate in resistance R, and there is no any normal. However, in very low temperature, also impurities can be participated in. However, in this video, we ignore them. Thank you. Thanks to watch.